Binomial distribution would be very useful to us when we're talking about differential or linear cryptanalysis or similar cryptanalysis techniques. So our aim is to talk about binomial distribution and its properties, but in order to do that, it is a good idea to start with Bernoulli distribution first. So consider an experiment with two possible outcomes called success S and failure F. Let X be the associative random variable where the success is represented with 1, and for this random variable, failure is represented with 0. So let probability of observing 1, in other words, success, has probability P, and the probability of the failure has to be 1 minus P, which is Q, because, this event has two possible outcomes, and we already said that the summation of all probabilities should be equal to 1. So if you say the success probability is P, the failure probability Q should be 1 minus P. So it can be defined like this. The probability density function is defined as P to the power X times Q to the power 1 minus X, where X is either 1 or 0. So it's either P or Q, in other words. And of course, you cannot observe any other value, so probability of observing anything else is 0. So let's talk about expected value. Recall that the expected value is the value multiplied with the probabilities. In this case, it is P, and the variance is P times Q. So you can easily compute them if you prefer. But now we can move on to binomial distribution. Consider n independent Bernoulli trials, each with probability of success is P and probability of failure as Q. So in the previous example, think about it just tossing a coin, but observing success. In other words, let's say heads has probability P and the tails has probability Q. So it doesn't have to be a fair dice. A fair coin. In the fair coin, the P and Q are always 1 over 2. But if it is not fair, this P can be something else. So Bernoulli distribution is no different than tossing a coin. But for the binomial distribution, we are now causing n coins. So this is the important part, because in cryptanalysis, we will be dealing n plaintext ciphertext pairs. So all of them will be independent Bernoulli trials. So consider again that success is P for a Bernoulli trial. In our experiments, by success, we will be talking about observing the statistical weakness we theoretically obtained, which we will call a distinguisher. So in our case, probability of S in terms of the P would be probability of observing the distinguisher. So again, let's go back to our example. We are tossing n coins. The sample space of this set of trials S is a set of n tuples, T1 to Tn, where you will be observing successes and failures. Again, where each Ti is either S or F. And the independence of trials gives that probability of observing any n tuple is probability of P to the m times Q to the m minus 1, with m being the number of successes. So if in this scenario, if you have, for instance, 5 successes, observing this probability is P to the 5 multiplied by, Q to the m minus 5, where you put those 5 successes in this n tuple. But those 5 successes can be in any different places. There are n possibilities, so you want to put 5 successes. So this means that you can have a combination of n with 5. So this is why we will have n choice m appearing at the beginning of our probability. So let me read the sentence and define it in a better way. If the aim is to observe the number of successes in n trials, then we know that for each m, which is the number of successes, remember, there are n choice m n tuples containing exactly m successes, right? Again, there are m places where you can put successes, and you have m success values. You can put them in this many different ways, which is n choice m, or combination of n with m. So the probability of obtaining m successes, where m can be anything less than or equal to n, between 0 of course, is n choice m multiplied by p to the m multiplied by q to the m minus m. So this is the important part. This is actually the binomial distribution. This is the probability density function. So we define it as follows. Actually, there is a typo here. This m should be x because we are defining it for x. Okay. Is that so? No. Let me think about it. Yes. Yes, this is a copy paste error from Bernoulli Distribution. I will correct it when I upload the slides. So the correct version should be nx, x, n minus x. Sorry for that. The expected value for the binomial distribution is n times p, and the variance is n times p times q. So these values are important. This n times p actually will be the main idea behind our statistical attacks like differential cryptanalysis or linear cryptanalysis, because we are going to perform n trials, and this is our probability of observing an event. So your expected value, which is the number of times you would expect to see that event occur, is n times p. So for this reason, is p, let's say if it is 1 over 10, you have to choose n larger than 10 so that this multiplication becomes larger than 1, and so that you can expect to observe that event in the real world. Okay, so this would be very useful for us when we are performing experiments. So we don't have much time to cover actually everything in probability theory. This is just like the 1 or 2 weeks of topics that can be covered in a probability theory course. I just gathered everything that we might need. So there are a lot of discrete random variables like Bernoulli, binomial, geometric, negative geometric, Poisson, and hypergeometric. So we only focus the first two, and the binomial distribution will be the most useful one for us. Also we have seen the uniform distribution, of course. Similarly, for continuous random variables, there are many continuous random variables. Again, we have continuous uniform distribution, exponential, Erlang, gamma, and normal distribution. I haven't covered it here, but normal distribution is actually useful in many areas of science, but it is also very useful in cryptanalysis. For instance, when we are trying to perform our success probability of attacks, where we are actually having binomial distribution, actually we will be using a theorem which maps binomial distribution to normal distribution, so that we can calculate the success probability in a better way. Actually, Ali Aydin Selçuk has a paper at Journal of Cryptology about this, where he solves this success probability computation problem. Because as you can see, for this probability, we will be working with numbers where n is 2 to the 128. As you might imagine, calculating such numbers is not easy. But once you can find a formula which allows you to approximate this value using normal distribution, it turns into a calculation of an integral instead of all of those summations.